Hello, children. One more lesson for today, and that is how do we rotate solids of revolution around horizontal lines that are not the x-axis. Okay, so we previously looked at how to rotate it around the y-axis. Rotating around the x-axis was our first lesson. So now what we're going to do is we're going to take how we rotated around the x-axis and we're going to shift that to rotating it around a line that is horizontal like the x-axis, but where it requires a little more thought about the function that's going to create the area for our disks. So this will be example 2, which will be find the volume, solid generated by rotating f of x equals 2 minus x squared around the line y equals 1. So what we're going to do is we want to start by looking at our function. Okay, so let's see, if we plug in 0 for x, we get 2 for y. Guess we'll do it in a different color so we can see it. Plug in 0 for x, we get 2 for y. If we plug in 1 for x, we get 1 for y. Plug in negative 1. Okay. If we plug in 2 for x, what do we get? Negative 2. Okay, so we have a parabola. Kind of looks like this. And what we know is that we want to rotate it around the line y equals 1. Okay, now what I didn't put in the question, and I guess I should have, is that I want to do this from y equals 0 no, that's not right. Y equals 1. To y equals 2. Okay, so the only part of the graph that I'm interested in rotating is the part of the graph that lies between y equals 1 and y equals 2. So the part of the graph that we're interested in is this part of the graph. So what I do not want to do is I don't need this other part of the graph here. So I'm going to get rid of this. Okay, because that's going to get in my way as I try to think about what's going to happen here. And I know that what I need to do is that I'm supposed to be rotating around this line y equals 1. So what's going to happen is that this entire shape is going to rotate, and it's going to end up coming down here, and we're going to end up getting, a shape that kind of looks something like this in the end. Now, what is different about this is that if we start to look at this, probably should have drawn this a little bit bigger. But what we can see is that the radius of our disk, which is always measured from the line we're rotating around, our radius is only going to go from here to here, or from, on this disk, from here to here. What we know is that the y value for the function, okay, the y value for the function at this point, the y value goes all the way from here to here. But the only part that we want as the radius goes from here to here. So the value of our function, the f of x, which is the green part, is not what we're going to be able to put into our equation. Because remember, our equation for volume is pi, our integral, r of x squared dx. Okay? We can see, and we could intersect it if we needed to, but we can see from our graph that our integral goes from -1 to 1, because that's where our 2 minus x squared graph intersects y equals 1. Again, if we couldn't see that on our graph, we could come over here, set them equal. We could solve this. Negative x squared equals -1, x squared equals 1, x is plus or minus 1. So it gives me my limits of integration here. But what I'm looking for is the radius number. So if the y value, the green part, is 2 minus x squared, and I only want the black part, what do I need to get rid of? Well, I need to get rid of this blue part, right? The blue plus the black is equal to the green. So I need to subtract something from the green part to leave me with the radius, which is the black part. Okay, so r of x is what I'm actually looking for. So how much is the blue part? What is that value from the x-axis to the blue line? Well, the blue part is always equal to 1 because it's a horizontal line there. So it's actually fairly simple if you draw it out and see what you're looking at. This is pi, -1 to 1, and in here I'm going to put the equation for that little black piece that's on my thing. And how much was it? It's 2 minus x squared minus the part I want to get rid of, which is the little blue part, which is always equal to 1 because I'm going from the x-axis to that horizontal line, so that distance, that height, is always 1 in this particular case. So we can go ahead and we can simplify this. Our integral from -1 to 1, 2 minus 1 just gives me 1 minus x squared dx. I have a choice. Okay, I can either well, no, that's not going to work. We're going to have to go ahead and square this out, because if we try to do a u substitution, we're not going to have the right value left in there. So we're going to have to simplify this a little bit more. So let's see, if we square this, what do we get? 1 minus 2x squared plus x to the 4th. Now we can go ahead and find our integral. This is pi times our whole answer, and our answer is going to be x minus 2 times 1/3 x cubed plus 1/5 x to the 5th from -1 to 1. So if we go and figure that out, again, I'm not going to multiply in the pi until I get done. If I plug all these numbers in, I'm going to have 1 minus 2/3 times 1 plus 1/5 times 1 minus this whole answer, which is -1 minus 2/3 times -1 to the 3rd plus 1/5 times -1 So if I put that in my calculator, I get 8 over 15 for that part, minus negative 8 over 15 for this part. So altogether, I get 16 pi over 15 as the volume of the solid that we generated here. So if we color in this whole area here, this whole shape in its three-dimensional form has a volume of 16 pi over 15. Hope that helps. Let me know if you need any help with the textbook questions.